Okay, so for this section, we're going to take a look at trigonometric substitutions. All right, and we're going to be using them to solve integrals that have these expressions here that you see on the left, right, where there's a root and then either of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared, right? And these are the substitutions that we'll be making. Now, in terms of what the domain of the angle theta, we won't worry too much about those. We'll assume that it is an angle does fall within that range, right? And the identity here for each corresponding substitution is kind of the reasoning for the substitution that we use, as we'll see, right? It's a way to kind of simplify what's inside the root so that I can just take the square root of a perfect square. So here, let me show you what I mean. Let's go through each of these three subs and why we're going to use them and how they're going to reduce our integral, right? So here we're just going to look at the substitution itself, and then in a later video we'll apply them to a solving integral. So the first one we're looking at, right, x equals to a sine of theta, right? Or in other words, sine of theta is equal to x over a, right? And then setting up a triangle. Here we have theta, right? And then we have opposite over hypotenuse, so x over a. And then the Pythagorean theorem leads me to this being the square root of a squared minus x squared, right? And if you see, if our integral has this expression, then when we make the substitution, x equals to a sine theta, we get a squared minus a squared sine squared theta. We can factor out an a squared, take the root of it, so we'll get a root of 1 minus sine squared theta. And again, the Pythagorean identity, that's our, excuse me, cosine squared, and take the root of that is a absolute cosine theta. But again, right, don't worry too much about the absolute, right? We'll assume that, just make sure that all the values that come out of there are going to be positive. All right, so that's for that first substitution. That's kind of the process that's going to happen. Whether that root is in the numerator or the denominator, right? That really is not going to matter, as long as that expression itself shows up in our integral, right? And then we see in the next one, right, if our substitution is a tangent theta equals to x, then we get tangent theta equals to x over a, right? And I like to draw this triangle because what we're going to see when we do find our integrals is the resulting integrals might be in other functions that are not sine or tangent or secant, right? So we need to be able to evaluate them to switch back to our x variable. So we need the triangle that'll help us out here. Right, so tangent is, what do we have here? Opposite over adjacent, which means that from the Pythagorean theorem up here, we get root of x squared, a squared plus x squared. Okay, and in terms of the substitution, right, we get, how that works is here equals to our sub a squared plus a squared tangent squared theta, factoring out then a squared, excuse me, the root of that is a, 1 plus tangent squared theta, and we see the result here is secant squared inside the root, but when we take the root, is secant theta. All right. Okay, and that's kind of how that works, right? We have this triangle here, right? Now one more here. All right, so our other substitution would be a secant of theta equals to x, right? Or secant theta equals to x over a. And again, our triangle, this is theta. All right, so it's hypotenuse over adjacent, a, and then here for this root we get x squared minus a squared, the root of that, right, from the Pythagorean theorem, right? Because all these, this is just right triangle trigonometry, right? And now we could see when we have something like x squared minus a squared, when I do my substitution, a squared secant squared theta minus a squared. Factor out the a squared, and we get secant squared theta minus 1. And then using our identity, tangent squared, the absolute value of tangent of theta. Okay. All right, and then I have my triangle to help me with any back substitutions when I do the integrals, where my resulting integrals will wind up in theta, but that's not what I want ultimately. Ultimately, what I want is integrals resulting in the result being in terms of my variable x. Okay.